Welcome to the Advanced Fluorescence Microscopy and Image Processing course. So today is the 14th lecture and we'll continue discussing about the digital images and camera technologies. And today mostly we will focus on the how the image is processed by CCD, EMCCD and SCMOS cameras. Okay, so let us begin with how the signal is processed in CCD camera chip. Okay. So see, this is a chip of a CCD camera. Here the chip is made up of 4 by 4 pixels. Okay, so total 16 pixels, just I have shown for the representation purpose. But as you know from the previous class, generally the CCD camera chip is made up of several megapixels, like 2 megapixels or 4 megapixels or 6 megapixels. Okay, so just for the representation, I have shown the 4 by 4 pixels. Now, as we discussed that this each pixel, what is the function of a pixel? Pixel converts photons into electrons. Okay, so let's say from your sample, this pixel converted photons into electrons. So there are 2 electrons. Here also there are 2 electrons. Here the signal was little high, so this pixel has 3 electrons. Okay, so this is basically the dot represents the electron distribution in all the pixels. Now the next step is, so this many electrons are produced per pixel by your CCD camera chip. Okay, now the next stage is the camera chip has to send this data to your computer, and computer should record that each pixel has this many electrons produced. So how it transfers the data from the pixel to the computers. So along with this active pixel array, there is a known as readout. There is a panel known as a readout register. So what happens once these electrons are produced? That these electrons moves to this readout register one by one. So first, this 4 pixel will send the electrons to this readout register. Then readout register will send these electrons to this output node one by one, and it will count the number of electrons per pixel. Okay. And then the computer knows that each pixel receives this many photons or the electrons. Okay, so first this lane is transferred. This lane is transferred here, and you see then the output node will receive electrons from this readout register one by one, and it will the computer will record that how many electrons are present per pixel. So this process of transferring electrons from the camera chip to the computer takes time. Okay, so it's a time consuming process as the electron pass through several lanes and then to the readout register. And this process makes the CCD camera slower in terms of the frame rate. Okay, because before transferring this electron to the output node, this chip cannot collect the another set of electrons or the photons. Okay, so it takes some time. Generally this time is in the range of milliseconds, and generally the CCD camera needs minimum 30 milliseconds to transfer all these electrons from the camera chip to the output node and to the computer. Okay, so what happens, let's say the read time, this is known as the read time of the camera, that how much time is required by your camera to process the image. So as I mentioned that generally the CCD camera takes 30 milliseconds to process your image, right? So that means your camera cannot capture the image, the next image before 30 milliseconds. Okay, so if you, let's say you are capturing the time-lapse movie, and if you ask your camera to capture the image at every 10 milliseconds, so it is not possible, because 30 milliseconds it needs to transfer the data. Okay, so it captures one image, then it needs 30 milliseconds to process those electrons, then it can capture another image, then it will take another 30 milliseconds to process the electrons. So basically you cannot go as fast as 10 milliseconds, but you can ask that camera to capture the image at every 30 milliseconds. Okay, or even more. That camera can capture the movies at every 50 milliseconds or 60 milliseconds, but not below 30 milliseconds, because 30 milliseconds is the camera read time. So even if you set your read time of camera, the exposure time you enter is 10 milliseconds. Okay, then also your first exposure will be 10 milliseconds, but the second exposure will be 30 milliseconds, third exposure will be 30 milliseconds, every other exposure will be 30 milliseconds, because your camera cannot process the data faster than 30 milliseconds. So with exposure shorter than the read time, the first exposure will be 10 millisecond, subsequent exposures will be equal the read time. So how to solve this issue? Let's say if you want to go for fast imaging, you want to go for every 10 millisecond imaging, how you can do that? So there is one option known as binning. Okay, and that is generally present in your computer software. Whatever the microscope software you are using, it always gives you an option of binning. So what this binning option does? This binning option does, see, it actually combines the electrons from 4 pixels, and all these electrons goes to the readout register as a 1 pixel. Okay, so this is how it can fast the processing. So instead of sending electrons from 1 pixel to the readout register, it will combine the electrons from all 4 pixels and send them all together to the readout register. And that way it can transfer the electron faster from camera chip to the computer. So this is known as binning, and binning can be of different type, like 2 by 2 binning, 4 by 4 binning. So when you are combining the electrons from only this kind of 4 pixels, it is known as 2 by 2 binning. So 2 in X, 2 by 2 in Y. So it is known as 2 by 2 binning. Suppose you are combining the electrons from 4 pixel in X, 4 pixel in Y, it is known as 4 by 4 binning. Or even if you combine the electrons from 8 by 8 pixels, then it is known as the 8 by 8 binning. Okay, and 1 by 1 binning is actually the real image. There is nothing like 1 by 1. It's a regular image without any binning. Whereas 2 by 2 or 3 or 4 by 4 or 8 by 8 binning actually mixes the electrons from different pixels. Okay. Now what are the advantages and disadvantages of this binning? So one advantage is quite obvious, that the processing will be faster. So the camera read time will be reduced. So instead of 30 milliseconds, your camera can now capture the image maybe at 20 milliseconds or even at 15 milliseconds. Okay. It provides higher dynamic range, higher signal to noise ratio. Why higher signal to noise? Because now the electrons from all 4 pixels will be represented as 1 pixel. So your electron counts are increasing. That's why your signal to noise will increase. Faster readout, and the dynamically change pixel size and aspect ratio. Okay, so that I will explain here. So now what you can see the difference in these 4 images, which are captured by 1 by 1, 2 by 2, 4 by 4 and 8 by 8 binning. You are seeing that your structures are getting brighter and brighter. Okay, but what else you can see? You are compromising on the resolution. Okay, because now you are combining the electrons from all 4 pixels and sending them as 1 pixel. So your computer cannot differentiate. Let's say in this image, there are these 2 pixels were having 5 electrons and these 2 pixels were having no electrons, but it will represent as 10 electrons. Okay, so that's why you are losing the resolution. So by using this binning option, you can go fast, but it is at the cost of resolution. Okay. Generally, in some applications, people may go up to 2 by 2 binning, but generally it's not a good idea to go for 4 by 4 or 8 by 8. Also, here you can see the size of your image reduces if you go for binning. So this is the size of a 1 by 1 binning, means basically that when there is no binning, the image size is like this. When you go for 2 by 2 binning, the image size reduces to this. When you go for 4 by 4 binning, the image size reduces to this many pixels. And if you go for 8 by 8 binning, the image size further reduces. Okay, so if you go for 2 by 2 binning, that will result in 4-fold improvement in signal, because it is the combined electrons from 4 pixels. So 4-fold improvement in the signal, twofold loss in resolution, because you're combining 2 pixels in X, 2 pixels in Y. So twofold loss in resolution, and twofold increase in signal to noise ratio, because signal to noise ratio will increase because now the electrons from all the 4 pixels will be represented as 1 electrons from 1 pixel, right? So there will be increase in signal to noise, and that's why you can see that as you increase the binning, your structure becomes brighter, but at the cost of resolution. So you should use binning with caution. You have to make sure whether the resolution is important for this particular imaging application or speed is more important. If speed is more important and resolution is not that important, go for binning. But if the resolution is also equally important, then you should not go for binning. So there are several types of resolution. Okay, we already discussed about the microscope resolution, right? But there are camera resolution, image resolution, monitor resolution, microscope or the lens resolution, and the true camera resolution. So what are the differences? So the camera resolution is the number of active light sensitive pixels. Okay, how many pixels your camera chip? So higher the pixel density, better is the resolution. So if your chip is 5 megapixel, that is better than 2 megapixel. Okay. Then the image resolution, number of pixels in the image. Okay. So how many pixels are there in the image? Then the monitor resolution. So the number of emitting pixels on our display. The microscope or the lens resolution. What is the smallest object that can be resolved or determined by the Rayleigh criteria? Okay, that we already discussed. And the true camera resolution. What is the smallest object that can be resolved based on the camera resolving power? Note that this is limited by the microscope. So let's say you want to separate two point sources of light as a two separate entity. The total resolution matters. The resolution of your microscope as well as the resolution of your camera. It is not good idea that you are using a microscope with very good quality optics and very high resolution, but your camera, you are compromising on the cost of the camera and you are buying some low-end camera, okay, which cannot provide the better resolution. So that's why generally very expensive cameras are used in microscopy to achieve the better resolution. Now coming to the how much area of the sample is captured by each pixel of the camera. Okay, so let's say this is your slide, this is your sample, this is a 10x objective lens, and here is the camera CCD chip, and this is one pixel of that camera CCD chip. So this chip is made up of so many pixels, but here I have shown only one pixel, and that one pixel, the size of that pixel is 6.5 micron by 6.5 micron. Okay, so in x-axis also it is 6.5 micron, in y-axis also it is 6.5 micron. So what I want to convey here is how much area of your sample is exposed to this 6.5 micron pixel. Okay, because there is a magnification in between. So let's say this one pixel size is 6.5 micron. So ideally, if you are using the 1x objective, it should capture the photons coming from the 6.5 micron area of the sample. But you are using 10x objective. So only 0.65 micron area of your sample is projected on this pixel of 6.5 micron. Okay, because of the 10x resolution, 10x magnification. Okay, so basically the idea is that 0.65 micron area of your sample is exposed per pixel, and what are the photons emitted by 0.65 micron of your sample will be captured by this pixel. Okay, that is known as pixel pitch. That is also known as the pixel size of the sample. Okay, so sample pixel size is 0.65 micron. That 6.65 micron area of the sample is projected per pixel. Now here also the Nyquist criteria helps for improving the resolution. So what should be the sampling distance in x and y to resolve your sample? Because see, suppose if these are your two objects, okay, and you use the camera chip with the pixel size of this, then what will happen? All this pixel will not show any electrons, but all these 4 pixels will produce some electrons, and it will produce the image like this, in which you are seeing the square because all these 4 pixels are giving the electrons, but you cannot resolve these two lines. Okay, but let's say instead you use the camera chip with a smaller size pixel, then what will happen? Like there are some empty pixels in between these lines, and because of that it will produce the image like this, in which you can see that there are two different lines instead of a square box. Okay, so how to determine this XY pixel size? So this we already discussed while discussing the Nyquist criterion for z-step size. That how you can determine while taking the z-step image that what should be the z distance for your image acquisition. Okay, so the same Nyquist calculator you have to use. I will show you here. So I showed you Nyquist calculator before. So here you can see this is the Nyquist calculator, and you have to select the type of microscope. So suppose you are using wide field imaging, then the numerical aperture of your objective lens is, let's say, 1.45. Your excitation emission wavelength, you are imaging GFP, and your excitation wavelength is 488 nanometer and the emission wavelength is 510 nanometer. The number of excitation photon is 1. Until unless you are using the 2 photon or multi-photon imaging, you should keep this value 1. And you have to mention the lens immersion refractive index. So whether you are using oil immersion or the glycerin immersion or the water immersion. So based on that, it will change the uh, refractive index. So generally we use the oil immersion objective lens. So I have kept selected oil, and the refractive index of oil is 1.515. Okay, and after keeping giving this information, we just have to press the button calculate. So it will calculate x, y, and z sampling distance for our sample. Okay, so see here it is showing x, y, and z, x, y, and z sampling distance for our sample. So what it is saying, you in x and y, 87 nanometer of your samples. So see, set your zoom and scanning step so that each pixel covers a xy area of 87 by 87 nanometer or smaller, and calibrate and set your z stepper so that it takes steps of 236 nanometer when acquiring a 3D stack image. Okay, so what it is saying that we already discussed that for z stack adjustment you have to see the z distance of 236 nanometer. So the microscope will capture image at every 236 nanometer. Okay, but in xy you have to set your zooms or the magnification in such a way so that 87 nanometer of the sample should be projected per pixel. Okay, so this is how you should maintain your xy sampling distance. 87 nanometer of your sample should be projected per pixel of your camera chip. So you have to adjust, use your objective lens or the zoom accordingly. Okay, let us go back to the. So if you adjust your zoom or the magnification in such a way that 87 nanometer of the sample is projected on your camera pixel, then only you can see the resolved structures like this. Otherwise, you will see this kind of resulting image. Okay. So coming to the camera resolution. Okay, so the camera resolution is given by this equation. It's a pixel size, and this is the objective magnification multiplied by 2.3. So there are three examples given for the currently used SCMOS camera. So there are two cameras, Prime BSI and Prime 95B. Those are the model of the camera, and this is also Prime 95B. But see, this Prime 95B camera uh, uh, has 11 micrometer pixel size, whereas Prime BSI has 6.5 micrometer pixel size. And here you are imaging with 60x objective, here you are imaging at 60x objective, and here you are imaging at 100x objective. Okay, so the idea why I am showing you this slide to give you the idea that how you should select the magnification. See, it is possible that even if your microscope has 60x and 100x objective, okay, and you have the 100x objective, so you will always go for 100x objective. That's not the case. Okay, you will unnecessarily do the oversampling if you go for the 100x objective. Okay, let's say for Nyquist we got to know that we need to resolve at 87 nanometer, right? So see, if you use this Prime BSI camera with 60x objective, what will be your resolution? 0.25 micrometer. Here, if you use the Prime 95B camera with 11 micrometer pixel size at 60x objective, your resolution will be 0.42 micrometer. Okay, and with this prime 95B camera at 100x objective, you will get the resolution of 0.25 micrometer. Okay, so resolution wise, the example 1 and 3 can give you better resolution, but you see for example 1, they have used 60x objective to match with this pixel size, whereas here they have used 100x objective to match with this pixel size. Okay, moving to the next slide and the new terminology, which is known as field of view. Okay, so currently Olympus, Leica, Zeiss offer models with 22 millimeter diagonal field of view. So field of view means how much area will be imaged by your microscope or by your camera. So here you can see the different field of view. Some cameras provide a rectangle field of view, whereas some cameras provide the square field of view. So this is prime 95B 25 mm, and this whatever this 25 mm is measured diagonally. Okay, like this from this end to this end. Then this is prime 95B prime BSI. It has 18.8 mm diagonal, and IRIS 15 model camera provides the field view of 25 mm. Okay, so this is the highest field of view 25 mm diagonal, which is offered by the Nikon. Okay, and how to calculate the field of view? So field of view in X, field of view in Y is depends on the pixel size, objective magnification, and the number of pixels in X, number of pixels in Y. And field of view diagonal is given by this equation. Okay, so for some applications, okay, you may need to image the larger areas. So in those kind of applications, you need to go for larger field of view. Let's say you want to image the entire tissue sample, then it's better to have the large field of view. But let's say you want to image small cells like bacterial cells or yeast cells. Okay, you do not really need the large field of view. Even the small field of view can also be enough. Okay. Now, what are EMCCD camera? So EMCCD stands for electron multiplied CCD sensors that have been placed for over 10 years and are used for extremely low light imaging applications. So as the name suggests, it's an electron multiplied CCD sensor. Okay, the same like CCD, but it has some electronic component by which you can electronically multiply the signal. Okay, so Photometrics introduced the first scientific grade camera in 2000, and EMCCD sensors are also back illuminated to give higher quantum efficiency greater than 90% and have large uh, pixels for improved photon collection. See, the pixel size of this EMCCD camera is 24 by 24 micrometer. Okay, this is the highest pixel size. Generally, for the current day SCMOS camera, the pixel size is 11 micrometer, whereas in the EMCCD camera, the pixel size was 24 micrometer, so it can collect photons from a larger area in the image. And the real advancements comes from the addition of an electron multiplication register to overcome the read noise. Okay, so generally in low light applications, the EMCCD camera are used. So when your objective is to capture the very weak fluorescence, then the EMCCD camera are useful. Let's say if you want to go for the single molecule imaging applications, then you will go for the EMCCD camera because you want to detect the fluorescence coming from single molecules. Okay. So how the sensor chip of EMCCD camera is different from the CCD camera? So in CCD camera, your entire sensor chip has the active pixels. So that means all the pixels can collect photons from the sample. Okay, but in EMCCD camera, the half of your sample, half of your camera chip is has the uh, inactive pixels. So see here uh, the pixels shown by white are the light sensitive pixels which can actually collect the photons from the sample, whereas the pixels showed in gray color, they are known as light insensitive pixels. So these pixels will not collect photons from the image or from the sample, but those pixels will help in transferring the electron and processing the electrons from this active pixel. So let's say in this EMCCD camera chip, these are the active pixels which can collect photons from this sample, whereas these are the light insensitive pixels. So they will not collect photons from the sample, but they will help in transferring these electrons. So in EMCCD camera, why they are faster? Because of this thing, they capture the image here, and then they immediately transfer the electrons from this area to this insensitive pixels, and again this area is available for capturing the next image. Okay, so that's why the EMCCD camera are faster than CCD, um, because of the presence of insensitive light pixels. Now that can be of two types. This is interline transfer. So either this inactive pixels, insensitive pixels can be arranged this way, or they can be arranged this way. Now coming to the EMCCD fundamentals. So how it works. So let's say there are two electrons captured by this active array. They will transfer it to this masked array, and this masked array will send it to readout register, and then the readout register will send this electron to the impact ionization. So this is the phenomenon known as electron multiplication. So impact ionization is nothing but kind of a photomultiplier tube. So when the one electron enters, it multiplies that electrons into many. Okay, so your signal will be enhanced. Okay, so even if you detect very low fluorescence from your sample, just one electron from your sample, but that one electron will be amplified into several before going to the analog to digital conversion, and before your computer reads it. Okay, so that's why this electron EMCCD camera are used for the low light application, so that even if your sample is weak, it is giving less fluorescence, but the signal will be enhanced because of this impact ionization, and it is known as the EM gain register. So when the EMCCD camera is attached to the microscope, you will see that there is one option in the software to adjust the gain of the camera. So gain of the camera is nothing but how much voltage you apply for the impact ionization. Higher the voltage you apply, it will be more amplification. Lower the voltage you apply, it will be less amplification of the electrons. Okay, so let's say by applying a lower voltage, if I can see my signal good enough, then there is no point of applying high signal, because it will also increase the noise also. Okay, so that's why you also have to adjust the gain of the EMCCD camera by imaging to adjust this electron amplification. Okay, so what is the unique property of EMCCD camera? Is the impact ionization. Okay, this active array and masked array, that is one thing, but that just increase the speed. But how it increase the signal, that is because of the presence of impact ionization, the electrons are getting multiplied so that the faint signal will become strong. Now there is a problem with EMCCD camera. So the gain that you are adjusting, okay, so when your camera is new, freshly purchased and never used, there is a straight line correlation between the actual gain and the set gain. So let's say if I am setting the gain at 200, I will also get the actual gain of 200. Okay, but what happens over the period of time, that impact ionization gets decay. Okay, and because of that, let's say the camera is 5 years old and you have used it frequently, then this impact ionization cannot produce as many electrons as it was produced when it was new, or the efficiency of producing the electrons or multiplying the electrons will reduce for this impact ionization. So what will happen if your EMCCD camera is old and has been used for several times, then instead of this linear correlation between the actual gain and the set gain, your actual gain will reduce. So even if I through software I set the gain to 200 like this, but see at 200 value I will get the actual gain of hardly 50 or 25. Okay, so that's why there is a decay in the EMCCD gain over the period of time. So because of that, what happened? Let's say you captured one image 5 years before for the same sample, and the image was very good quality. You can see your single molecules here. Okay, but after 5 years, using the same microscope, same camera, same sample, you will see the image like this. Okay, and that is not because of your sample. Your sample is still the same, but that is because of the decrease in the gain, in the actual gain of the EMCCD camera. Now coming to the CMOS technology. So CMOS as a technology is an old as CCD, but was not considered as a sensor capable of light detection until 1992 by Dr. Eric Fuson, a scientist at NASA's Jet Propulsion Laboratory. CMOS technology offers or it differs by amplifying signals at an individual pixel level and distinguishing the value of all columns in parallel. So generally the CMOS sensors are used for fast imaging applications. And how it achieves the fast imaging? By parallelization. Okay. So all the individual pixel has its own amplifier, has its own capacitor. So the data is produced and processed immediately from each of the pixels. I will show you how the pixel looks like in CMOS camera. So see, this is the pixel chip of the CMOS camera, and here the photon is coming, it is converting into electron, and each pixel has its own capacitor and amplifier, so it will produce some voltage. Okay, and each lane has its own analog to digital conversion unit. Okay, so generally in EMCCD and other CCD camera there is only one ADC, whereas here there are four ADC, means one ADC per lane, so that the processing will be faster and all four ADC will send the signal to PC. Okay, so multiple collecting beams are there, and because of that the image processing is faster, and that's why the SCMOS camera are used for fast imaging applications. EMCCD camera are used for the low light imaging applications, whereas the CMOS camera are used for the fast imaging applications. So advantages of scientific CMOS camera, which is known as SCMOS. Okay, so low noise, 1.3 electrons of read noise compared to 6 electrons on CCD. Okay, so the read noise is less. Rapid frame rate up to 100 frames, 100 FPS, that is frames per second for full frames. Large field of view, high resolution, because the pixel sizes available are from 4.25 micron to 11 micron. So pixel sizes are smaller than EMCCD. EMCCD pixel size was 24 micrometer, whereas for SCMOS the pixel size is 4.25 to 11 micrometer. Wide dynamic range and no degradation, unlike EMCCD camera. So as we just discussed that in EMCCD the gain decreases, the actual gain decreases over a period of time because of the decay in the impact ionization. Whereas in SCMOS camera, whether you used it 5 years before or you are using the same camera and same microscope now, the image quality will be the same. There is no decay. Okay. So here I have shown the comparison of an image captured by CCD versus scientific CMOS. So this is captured by the CCD camera, CoolSnap EZ, and this was captured by the SCMOS camera, Prime 95 or Prime BSI. Okay, and see both the cameras were used with the same exposure time, 10 millisecond exposure, 10 millisecond exposure. But here you see the read noise is more, the 8 electrons is the read noise, whereas here 1.3 electron is the read noise. So you can see better signal to noise here compared to this one. Okay, CMOS sensor is larger compared to CCD. The CMOS sensor chip is 18 mm diagonal versus 8 mm CCD chip. As scientific CMOS has 72 to 82% quantum efficiency compared to the 60% of CCD. So as I mentioned, what is quantum efficiency? The quantum efficiency is how many photons are converted into electrons. So CCD camera have the quantum efficiency of 60%. That means 60% photons hit the pixel, and sorry, if 100 photons hit the pixel, 60% of them are converted into electrons. Whereas in case of CMOS, the quantum efficiency is 72 to 82%. That means 82% photons are converted into electrons by these pixels. CCD has far higher read noise, 8 electrons compared to 1.3 electrons on CMOS, and CCD offers 10 FPS full frame imaging speed, whereas CMOS offers 100 FPS full frame imaging speed, because here the processing takes long time, so you cannot go for fast imaging, whereas in CMOS there are multiple ADC, analog to digital converter, and each pixel has its own capacitor and amplifier. Because of that the speed is increased due to parallelization. Okay, here is the difference between EMCCD versus SCMOS. the pixel size of an EMCCD is 16 micron or even sometimes 24 micron against the 6.5 micron of scientific CMOS. So you can have 6x more signal per pixel. Then the EMCCD also have 92% quantum efficiency at base wavelength. Base SCMOS is 82%. So for 100 photons, you get 10 extra electrons. But this is not true these days, because these days the SCMOS cameras are also available with 95% quantum efficiency. And EMCC do not have excess noise, which is an increase in short noise by a factor of 1.4 in the noise equation. And for 25 electrons of signal on the scientific CMOS, you would have 5 electrons of short noise. On EMCCD, this will be 7. So the short noise will be more in case of EMCCD. Okay. Now, coming to another terminology which is sometimes used as a back illuminated CMOS. Okay, so what is back illuminated and what is front illuminated? So let me show you this diagram first. So cameras are available in two configuration. Either they are front illuminated or back illuminated. So in front illuminated, you can see these are the lenses which collects light from the sample, and there is some wiring here which is known as the metal wiring. Okay, and this light has to pass through this metal wiring to reach to the detector. This is photodiodes. Okay, light reactive surface is here. So the light reactive surface is here, but on top of the light reactive surface, there is some metal wiring, and your light has to pass through this metal wiring to reach to the light receiving surface. And because of that, what happens? Some of the light gets diffracted here or reflected here, right? So after 4 rays, only 2 rays are entering. So this reduces your quantum efficiency. Okay, but uh, these days people have developed back illuminated camera, so in which you can see this light reactive surface is just next to your lenses. So all the 4 rays can reach to the light reactive surface, and the metal wiring is on the back side, and that's why it is known as back illuminated structure. And this is known as the front illuminated structure, in which the metal wiring is on top of the uh, light reactive surface, and that's why all the photons cannot reach to the detector, whereas here all the photons can reach to the detector because the metal wiring is on the back side of the camera. And this kind of camera can obtain 95% quantum efficiency, means they can convert 95% photons into electrons. Okay, and these days all the this prime 95V, prime BSI SCMOS camera, they offer 95% quantum efficiency because of the back illumination. Okay, so here I have shown one example, the image comparison between EMCCD and SCMOS. So this prime 95B is the SCMOS camera, whereas this is the image taken by the EMCCD camera. Now if I ask you that find out the difference between these two images, can you see any difference here? The answer is no. Okay, one is the EMCCD camera, one is SCMOS camera, and the image has been taken with the same exposure time of 30 milliseconds. Okay, and you cannot see any difference between these two images. And what I want to show you here is the SCMOS camera is as good as the EMCC camera, because these days the SCMOS cameras are also available with 95% quantum efficiency. Okay, previously the SCMOS cameras were available with only 82% quantum efficiency, and the EMCD cameras were available with 95% quantum efficiency. But these days these SCMOS cameras are also available with 95% quantum efficiency. So let's say if you have to buy a new camera, you will ideally go for the SCMOS because it provides high speed also, as well as low detection sensitivity. Okay, even the low fluorescence also it can detect because of the 95% quantum efficiency. So here you can see some comparison between CCD, EMCCD and scientific CMOS camera. Okay, and every camera has its own place, some advantages and some disadvantages. If you just compare the price, then obviously the EMCCD and SCMOS are on the expensive side, whereas CCD is comparatively cheaper than the EMCCD and SCMOS. CCD is good for bright samples like the if your fluorescence is bright, you can go for imaging with CCD camera. Otherwise, for very low light, you should go for EM-CCD. And even these days, you can use the scientific CMOS also. Here there is a high read noise, here very low read noise, and here it's a low read noise. In terms of speed, scientific CMOS is the very fastest one, and this is fast and this is slow. In terms of pixel size, here CCD camera has small pixel size, EM-CCD have the large pixel size, and scientific CMOS have the balanced pixel size and optimized for Nyquist. So that is another advantage of the scientific CMOS camera, that this pixel size are optimized for 40x, 60x, and 100x objective lenses. In terms of field of view, SCMOS have the largest field of view. We already discussed about the pricing and which kind of application you should use this camera. So just for the documentation purpose, if you just want to show that this cell expresses GFP and some red fluorescent and some blue fluorescent, okay, CCD camera is good enough. But if your application needs some kind of highly sensitive or weak fluorescence detection like single molecule imaging, TURF, or spinning disk kind of imaging, you need EM-CCD camera. And for the applications where speed also matters, you should go for scientific CMOS for high speed FRET, high speed TURF, super resolution, and light shield and wide field imaging. Okay, so based on your applications, you should select the camera. And again, coming to the speed, so camera speed or frame rate is dependent on the following parameters: the exposure time, digitization rate, binning, and region of interest. So the speed of CMOS camera is dependent only on the exposure time and region of interest. So if you really want to go for the very fast imaging, you can go for SCMOS camera by reducing the region of interest. Okay, but binning and digitization read time is not limited for the CMOS camera. Okay, so here I will show you how to go faster with imaging speed. So let's say suppose for some application you really want to go for very fast imaging. Very fast means let's say 10 at every 10 millisecond or every 15 millisecond you want to take your time lapse image. So there are three ways to go faster. The first one is obviously you lower your exposure time. Suppose you are keeping your exposure time 50 milliseconds, you cannot go faster than 50 milliseconds, right? Because camera will expose the sample for 50 milliseconds, then it will take maybe another 10-15 milliseconds for processing. Okay, so you cannot go faster than 60 or 75 milliseconds. So first thing to go faster is go for the low exposure time, either by increasing your light intensity or by using EM-CCD or SCMOS kind of detectors. Then use small region of interest. Okay, so let's say suppose here your area of interest is only this portion. Okay, don't go for imaging the entire field, because camera needs to process all these electrons from so many pixels, right? So you can just crop this area and ask the software to image only this area. Okay, so let's say with this entire field you can go for 10 frames per second, but if you select half field, then you can go for 20 frames per second, because camera has to process the electrons only from the half number of pixels, not from all the pixels. Okay, so by reducing the region of interest or by imaging in a smaller area, you can go faster. And the third option is use binning. Okay, sacrifice on spatial resolution for faster frame rates and reduce the data. Your size of the image will be smaller. Okay, so binning you can use for going fast, but here you will compromise on your spatial resolution. Okay, whereas here you will not compromise on your spatial resolution, but you will get high speed also. Okay, so these are the three options which you have to critically determine for going for fast imaging applications. Okay, with this I would like to end today's class, and in the next lecture we will discuss about ImageJ Fiji based image processing and data analysis. I will ask you to install the Fiji or the ImageJ on your laptops, and I will also share some of the sample images for data analysis. Thank you.